Welcome to our Wolfram Innovator Awards 2024. This is part of our Wolfram Technology Conference, which is virtual this year. So those of you who are part of the conference, hope you've been having a good time at the conference. Those who are watching this from the outside world, welcome to our event. So for the last 36 years, we've been making Mathematica and Wolfram Language and our other products like System Modeler and so on. A recent product, and we build these as tools, we put them out in the world, and then the question is, what do people do with them? And it's always very exciting to hear about and see things that people have done with the tools that we've spent so much effort building. And our Innovator Awards are an annual opportunity to recognize some of the very interesting things that we know about that people out in the world have been able to do with our tools. And I have to say, I always find this particularly interesting because I like learning about everything, and it's particularly pleasing when it's things that have been made possible or helped by our technology. But one of the downsides for this year is that we normally, when we do these conferences in person, we have the opportunity to have lunch with our Innovator Award winners. Lunch usually has a well-defined endpoint, but we were doing virtual lunch, which didn't have such a well-defined endpoint. So I spent the last quite a few hours chatting with our various Innovator Award winners of this year and learning a lot of very, very interesting things. But my plan and then I will prepare remarks to make about each of them was exploded by being too interested in all the things that people had to say. So I will warn you that I'm going to be talking really off the cuff here and describing, so this won't be as systematic as sometimes these things are, but I think it's I want to give everybody the opportunity to hear something about the interesting kinds of things that our Innovator Award winners have been doing. So, without further ado, perhaps we should move to our first award of the evening, which goes to, let me just start sharing the right screen here. Our first award of the evening goes to Michael Berry, or more properly these days, Sir Michael Berry of the University of Bristol. And I will say, I first ran into Michael Berry a very long time ago, probably 1978, 1979. He came to give a talk at Caltech and was talking about things that seemed very 19th century, about optics and about the pattern that you see on the bottom of a swimming pool when the sun is shining through the ripples on the surface. But he was connecting it to what was then a very talked about field of catastrophe theory, and talking about the things that people in the 19th century didn't know about optics and about the formation of caustics, the kind of lines of brightness from light and so on. Well, then I know that I view much of Michael Berry's work as being extremely elegant mathematical physics of the kind that one sees in lots of old physics textbooks, because it was done in the 19th century, except that there were pieces that didn't get done in the 19th century. And the reason they've got done now is because of Michael Berry. And I'd like to believe that some of what's happened there in the hundreds of papers that Michael has written over the years, that some of what's now been possible has been made possible by Michael's use of Mathematica and Wolfram language. Michael was just telling me that the airy function, which is a mathematical function that shows up in lots of places, originally introduced by George Airy, I think in the 1830s, that George Airy couldn't compute the Airy function. It took a few years more for people to be able to even approximate it. Now, of course, in Wolfram language, you just type Airy AI and you can compute the Airy function. A piece of trivia I didn't know that I just learnt is that when you have when you have a boat going through water, it makes this kind of shock of waves. And if you're in a little boat in the wake of this of the big boat that's making this V of waves, the wiggles of that of your little boat as that V goes past you, those wiggles are in an area function. They have the area function has wiggles. You feel those wiggles in the small boat. Well, I think Michael Berry first got Mathematica back in 1988, the year it came out, and he's been using it ever since in doing, as I say, things that just missed the 19th century and had to wait for the 20th or 21st century for Michael Berry to do them, in optics, in quantum mechanics, in other areas of very, very elegant areas of applying sort of the methods of mathematical physics. And I think it's when we have spent effort to put mathematical special functions into Wolfram language, it's great to find out what a good home they find in the work of people like Michael Berry. It's also very interesting to see the extent to which it's possible to actually get solutions, analytical solutions, in terms of things like special functions to these kinds of problems that are problems that show up in practice. But I know that Michael Berry has also used Wolfram language extensively in numerical computations to just do what amounts to experimental mathematics, to just sort of find out what's true, and then be able to go and make more analysis. He was just telling me about something which, again, is something that you kind of think would have been studied in the 19th century, what he was calling curl forces, where you have a field of force that is not derived from a potential, like the electric potential gives you the electric field by taking a gradient and so on. These are force fields which are not derivable from potentials, and that when one actually solves the equations of motion for such things, that one sees all sorts of elaborate behavior, which no doubt Michael Berry is analyzing for us. I know over the years, Michael Berry has done many things that have seen public visibility in terms of understanding things about rainbows and glories and other kinds of atmospheric optical phenomena, things in quantum chaos. But perhaps one of the things for which he is in some ways the most famous were some experiments on magnetic levitation of frogs, which have been sort of caught the public imagination, but are really a story of very interesting mathematical physics underneath. In any case, so our first award of the evening goes to Berry. I can there we go.
Well, okay. Oh yes, here I am. Well, good.
Thank you.
Thank you very much. It's much appreciated.
Thank you for all of the interesting things that you've done.
Thank you.
Right, let's see. Well, our next award of the evening, operate properly, goes to Mauro Da Lio of the University of Trento in Italy. And Mauro is concerned with self-driving cars, and has been using Mathematica, Wolfram language, and I believe system modeler to as part of an EU project to study the problem of self-driving cars. I gather his earlier work was in multi-body dynamical systems and equations of motion and so on, and in control theory. But in more recent times has been concerned with the problem that so many people have been concerned with, although I think he's been working on it longer than most, of how do you make a car that can drive itself? And let's see, let's share the right thing. Sorry, I'm just looking at my what did I share? Sorry, I'm confusing myself here. There we go. I think I was not sharing the screen. I apologize for that. And we're talking about Mauro's work, and we see a lot of interesting control systems there. Mauro was telling me about some of the issues of self-driving cars and the kinds of modeling that one can do, and particularly his interesting analogy with kind of human control systems and what we humans do and how we humans think about the problem of taking actions. And I think the thing I find interesting is that I've well, quite a lot of companies that make self-driving cars make use of our technology, and I occasionally hear some of the things they're doing. But Mauro is sort of the first time I've really heard a discussion about how the way that we humans plan actions with our motor cortex and basal and different parts of the brain and so on, and thinking about that in correspondence with the way that one has to think about self-driving cars doing what they do. In particular, thinking about the way that we humans sort of imagine actions as something that one should kind of map onto what happens in self-driving cars. And particularly, I was struck by Mauro's ideas about the fact that sleep is important to learning things, and the fact that the kind of rehearsal of actions in dreams and in other phases of sleep can be important in being able to sort of know what to do if this or that thing happens. And so it's been the idea of using neural nets to capture those kinds of things which humans do in those ways seems very interesting to me. It's Mauro was commenting on some of the really challenging aspects of self-driving cars that have to do not with the immediate, can I merge into this lane of traffic, but more in the much more distant planning of there's a truck driving down the freeway in front of me, and it's got this thing on it that looks like it might fall off. Maybe I should hold a larger distance. And the analogy of that kind of thinking with the kinds of things that we rehearse in dreams. So I thought that was very interesting, and it's I gather Mauro has been using Wolfram language since version 6 or so to study this kind of both dynamical systems and their correspondence with actual sensory motor activity in humans. So our next award goes to Mauro Da Lio. And oops, there we go. Thank you very much. Very interesting work. Let's move on here. And our next award, I shouldn't keep on saying of the evening because it's I only know what time zone I'm in. But our next award goes to Pedro Fonseca. the Suez Company. I learnt that the Suez Company was the company that built the Suez Canal. So that was a while ago. And now it's a large company concerned with environmental engineering around the world, and particularly with water. Pedro is involved with water resources and both drinkable water and wastewater, and has been using Wolfram language since version 5.2, and for many different kinds of things. He was explaining to me that he's had an opportunity to make use of, he thinks, almost every part of Wolfram language except the quantum part so far. And that he had was at first using it for sort of traditional mathematical modeling kinds of things, but told me the story of having to work out at some point how to orient some particular water treatment system, and needing to know for that what were the prevailing winds in a particular area, and realized, well, actually, we have data, just a function, wind vector data, that tells you that. And so he was able to immediately use that and get a conclusion. I gather that in the process of purifying water, that there are many issues, both physical, chemical, biological, and fluid dynamics involved with that. And I remember when I was a kid seeing, at the town where I lived, Oxford in England, seeing the water treatment plant and being a little bit horrified by the fact that the main thing that was used to purify the water was just you let it settle in a tank for a day and all the bad stuff drops out. But I learned today that this phenomenon of flocculation, where smaller particles aggregate to bigger particles, that's a piece of one of the many techniques that are used. So it isn't really just a question of you put the water in the tank and you let things drop out. There's a process for using interesting physics to accumulate to bigger particles. Those things drop more quickly. Now, I gather that Pedro has not only been using Wolfram language and Mathematica, but also System Modeler. The main problem, the main project, is the design of water treatment systems. And I gather that's typically sort of from beginning to end might be a decade-long process. And apparently every city, every water treatment system is sort of a custom problem. They all have different issues and they all require different analysis. And Pedro has been using our technology along with his team to do that analysis now for many years. So with that, our award goes to Pedro Fonseca.
Thank you very much, Stephen.
Thank you. Well, our next award goes to Guillermo Sanchez Leon. Who is, I gather, recently, in principle, retired from Salamanca University in Spain. A long-time user of Wolfram language since 1991, I gather. Guillermo was actually a visiting scholar at the company in 1999. And one of the places where I've seen his work is a book that maybe we have illustrated here. Oh, yes, we do. Mathematica Beyond Mathematics. That's a very nice topic and a lot of very interesting examples. Guillermo spent, I gather, many years in the nuclear industry in Spain, and particularly involved with fuel rods and taking uranium used for reactors and putting it in the right configuration to be used as a fuel rod, and the analysis of those kinds of things, and doing let's see, also working on other aspects of the nuclear industry, from dosimetry, nuclear medicine, and so on, and studying the equations that are necessary to do that. Now, I gather that in his retirement, Guillermo has turned to medieval astronomy and has been studying particularly the works of Spanish astronomers from the Middle Ages. He was telling me that from Ptolemy, who produced his famous Almagest book in the 1st century AD, I think, 2nd century AD. One of the next notable moments was Alfonso in Spain producing more accurate tables that were not eventually overtaken until Tycho Brahe and Kepler several centuries later. And I gather Guillermo has been starting to study those things, and I hope he has a chance to use some of our recent astronomy capabilities in studying the observations and so on that went into those tables. I have to comment, my son Christopher, who happens to have been interested in Babylonian astronomy, was studying that recently, just a few weeks ago, and comparing the observations the Babylonians made, well, nearly 3,000 years ago, with the calculations that we can do. And he found a bug in the position of Jupiter extrapolated backwards based on what we had. So sort of an interesting bug report of this must be wrong because the Babylonians in 800 BC or something said it was different. In any case, we wish Guillermo a very interesting time in studying medieval astronomy, and astronomy is one of those lovely areas where you can take something that is sort of a completely modern piece of celestial mechanics and expect that it will apply all the way back to things that science really works, physics really works in that case. You can really do both you can really say with precision, you can compute with precision what somebody will have seen in in the time when the University of Salamanca was founded. I think he said that was in 1218 AD, one of the earliest universities. Well, so our award goes to Guillermo Sanchez Leon. Thank you very much.
Thank you very much.
Thank you. Well, our next award goes to Andrew Lutken of the Technology Innovation Institute in Abu Dhabi. And Andrew has had a long career in theoretical physics, except that now he's running an organization which is actually building practical experimental quantum computers using superconducting techniques. And Andrew has been using Wolfram language since the very beginning, 1988, and to do things in particle physics and quantum field theory and Calabi-Yau manifolds. And I see I hadn't had a chance to chat with him that worked with a person called Graham Ross, who I knew many years ago, constructing the first predictive model of the quantum Hall effect, using another one of my old favorites, the nonlinear sigma model. That's wonderful history, and I have to say it's always very inspiring when people can make the jump from theoretical physics, like studying nonlinear sigma models, to practical physics with cryostats and manufacturing superconducting Josephson junctions on silicon substrates and so on. So I'm very impressed by that. I gather last 3 years, Andrew has been working in Abu Dhabi, and they're hot on the trail. Well, hot as one gets if one's operating in the milli-Kelvin regime, of being able to produce superconducting quantum computers, I think there are. My own suspicion is that there's lots of very fascinating theoretical physics hiding in what people think of as the awkward engineering noise of quantum computers. And I would suspect with Andrew's approaches to theoretical physics and to the practicalities of building quantum computers, that he'd be very well equipped to be the person who gets to discover sort of the analog of the diffraction limit for what limits quantum computers. But we'll see. Or maybe there will be a way found to break through the noise and get purely to those quantum effects that one wants to see. Well, so our next award here goes to Lutken. Well, Andrew has a chance to turn on his camera so we can say hello. Thank you very much. Very interesting work. I shall be very interested to see more about what happens with your quantum computers. All right. Well, our next award goes to Thomas Wallek of Graz University of Technology in Austria. And oh boy, I didn't get to talk about all these amazing pictures from Andrew. Yeah, well, something to study separately. So Thomas has been working in chemical thermodynamics and building for educational and other purposes using Wolfram language to build simulations and presentations about chemical thermodynamics. Not apparently, yes, he was telling me that his first exposure to Wolfram language was through a student who was able to take some complicated expression that had arisen and just use simplify, and simplify gave him a polylogarithm function. I have to say polylogarithms were always a favorite kind of special function of mine. They show up in the evaluation of Feynman diagrams in particle physics, which happened to be kind of my personal early entry into really needing to use computers to do mathematical computation. But Thomas also got to see a polylogarithm in the wild, and I gather that hooked him on the value of Wolfram language and Mathematica as a tool to study things. So, in addition to research, use Wolfram language as part of a technology-enhanced learning effort at Graz University of Technology, and for the purpose of giving students, as many of us find, the effort to visualize and the ability to visualize things is just very critical to understanding. And I gather Thomas has been providing technology to his students as a way to have them understand chemical thermodynamics as they will later apply it as process engineers or chemical engineers or whatever in the future. And that's a terrific use. Also, I gather that it's been involved in a bunch of developing explicit packages for Gibbs ensemble Monte Carlo simulations, and was asking me about has been using compile functionality and really wants to use function compile more, and has been finding that the kind of ability to visualize things in Wolfram language has been sort of critical in guiding the way to create these kinds of simulations, and I gather has made some very nice packages for Monte Carlo simulation in the language. So our Innovator Award goes to Thomas Wallek.
Thank you, Stephen. I'm very proud, and it's a pleasure to receive this award. Thank you.
Thank you very much. From thermodynamics to particle physics, mathematics. Our next award goes to the LieArt team. That's Robert Feger, Thomas Kephart, Robert Saskowski. And I think the two Roberts, I believe, are here with us. So, you know, I've had on the to-do list for Wolfram language, do Lie algebra, deal with Lie groups. That's Lie groups are kind of the continuous groups, like the rotation group in 3 dimensions is the group SO3, and there's a classification of Lie groups that tells one there are particular kinds of groups that can occur. And I've had on the to-do list for Wolfram language handle Lie groups since 1986, when we started building Wolfram language. In fact, it goes even further ago than that. When I was building SMP, the forerunner to Wolfram language, starting in 1979, I had Lie groups on the to-do list of things that I wanted to be able to handle. And part of the reason for that was that I started my scientific career working in particle physics. And in particle physics, I was working on things like quantum chromodynamics. In quantum chromodynamics, there's this color symmetry, and there are three colors of quarks. There are 8 colors of gluons, and when you try to work out probabilities for interactions, you have to kind of match up all the indices of all the different ways that those different colors of gluons can combine, and so on. And this becomes an adventure of group theory, and relates to and one's interested in those kinds of things. Well, I had long wanted to automate the process of doing those calculations, and now LieArt has done that, and it's a package that's widely used by folks to do the algebra computations. I think I gather from Robert Feger that he got introduced to Lie groups through the group I think he said SU9. It's a very exotic Lie group. I'd never heard of SU9 being used before. See, in particle physics, the standard model of particle physics is SU3 cross SU2 cross U1. Those are particular Lie groups. And as people tried to make grand unified theories in particle physics, the idea was you want to get SU3 cross SU2 cross U1, but those could be subgroups of a bigger group. And so SU5 was one candidate, SO10 was another candidate. Those are successive sort of supergroups. And then we go beyond that, you get to, I think, E6, E7, the exceptional Lie groups, and so on. And this whole question of sort of what are the structures that you get with these different assumptions about the Lie groups that describe the symmetries of particle physics, was something that's been of great interest for a long time. The thing that is probably the most notable is once you have one of these Lie groups, there are representations of the Lie group, that is, represent them in terms of matrices or something like that, collections of matrices where the transformations, where the matrices kind of describe the basic transformations of the Lie group. And there's sort of a question of, well, how many matrices do you have? And that how many matrices do you have corresponds to how many particles how many distinct kinds of particles you have in that particular irreducible representation of the group. So for example, in the group SU3, there's the 3 representation gives you the quarks, the 8 representation gives you the gluons, and so on. So it's of interest to understand kind of what the representations are and the characteristics of those representations. And that's what LieArt computes for one. And it's the question, I was curious what kind of methods one really gets to use to do those computations. And I gather it's really mostly a story of combinatorics with some eigenvalues and so on. It's rather intricate, and it's something where there have been books of tables, but it's not even clear the books of tables are right. And there are many different conventions for how you define all of these different constants that show up in the analysis of Lie groups. And LieArt does that all consistently, does that in Wolfram language, and does that sort of on demand, whatever group you need, whether it's SU9 or something else. And I have a strong suspicion that there's some LieArt usage in my future as we try to understand the implications of our physics project and try to understand how kind of the structure of this hypergraph that represents sort of, well, space and everything in it, how that structure breaks down into a part that corresponds to ordinary space and a part that corresponds to kind of the internal symmetries that exist that we know about from particle physics and so on. And as we try to understand just what kind of Lie group-like structures emerge, I have a suspicion that there's some LieArt usage in my future. Well, so I'm really glad that Robert and Thomas and Robert number 2 have created LieArt, so people like me get to use it. So our award here goes to the creators of LieArt. Thank you very much.
Thank you very much. It's a great honor
Thank you.
to receive this award.
Our next award goes to Sebastian Mizera of Princeton University, I think, moving soon maybe. So Sebastian, I particularly aware of a survey that he wrote about the S matrix in particle physics. And this paper has just very beautiful pictures in it and looks like a very beautiful exposition of the S matrix. And it's been on my to read list for a number of months. And I've now gotten another push to actually read it. It's a funny thing because when I got involved in particle physics in the mid-1970s, the S matrix was just going out of fashion. There had been sort of two approaches to studying particle physics in earlier years. One approach was to use quantum field theory and to try and use Feynman diagrams and to try to work out the kinds of things that, for example, LieArt can be used for, where you're studying, oh, there's this individual particle and it interacts in this way, and you have a collection of sort of elementary interactions and you're adding up the effects of those elementary interactions. That was approach number one. Approach number two was the S matrix approach, where you just say there are a bunch of particles going in, something happens in the middle, and then there are a bunch of particles coming out. And the something happens in the middle is described by the S matrix. So invented originally by Werner Heisenberg, who sort of got frustrated in trying to understand what happens in the middle and just said, let's just define this big matrix that says, based on the incoming states, what will the outgoing states be? Well, the S matrix in the last 10 or 20 years has sort of come back into fashion, partly because it was realized that there were models where it was possible to work out precisely certain scattering behaviors without using sort of the approximations of Feynman diagrams. I have to say, I knew Dick Feynman, inventor of Feynman diagrams, for a number of years, quite a number of years. And one of the things he would always say, particularly when he knew that I'd spent a bunch of effort using computers to work out things with Feynman diagrams, he would always say, these Feynman diagrams, he called them Feynman diagrams, were kind of a stupid idea. There's got to be a better way to work out what happens in these theories and quantum field theory and so on than to use these diagrams, which take so much computational effort. Well, there's now starting to be some glimmer of an idea for how that might work. And so that's sort of the reason for the repopularization of the S matrix. And the S matrix, from a mathematical point of view, and this is something that I believe Sebastian has made quite a study of, is the analyticity properties. The S matrix can be thought of as a function of many complex variables with very complicated smoothness analyticity properties that are sort of forced upon it by various requirements of causality, that sort of effects can't travel faster than light and so on, forces certain characteristics of this function of many complex variables. And that's an adventure that people had sort of started in the 1950s to early 1960s. And with all the advances in mathematics, and I'd like to think with the advances in our technology for handling that mathematics, there's sort of the better chance to really understand what's going on now. I gather that Sebastian has taken kind of Heisenberg's thinking about the S matrix to an extreme. Heisenberg was like, we don't know what's in the middle there, let's just make it a matrix. Well, we live in modern times, and when we don't know what's there in the middle, let's make it a black box. In today's world, that would be, let's use a neural net to represent that. And so Sebastian has done the very interesting thing of thinking about how do you use a neural net to essentially approximate the S matrix? And if you know certain scattering probabilities and so on, certain examples of scattering probabilities, can you just say, let's just make an S matrix out of neural networks and have that be the way to calculate things? And there's this question of sort of what will the neural nets be able to do, and to what extent do they correspond only to things that humans are able to do, or are they able to do things which are sort of interpolations that are the domain of physics that have nothing to do with the things that humans are able to do? Anyway, that's something that Sebastian has been studying. He was also telling me about some recent work he's been doing about scattering. But usually when we think about scattering in particle physics or something, it's like you collide an electron and a positron, or you collide two protons. But instead, Sebastian is involved in the business of asking, what if you collide two black holes? What will happen then? And there's sort of the possibility that kind of when the black holes are at least far enough apart that you can use sort of a perturbation analysis that's analogous to the Feynman diagram idea from particle physics to see what's happening. And then as the black holes get closer, you get to do the kinds of things that you do in particle physics, where you're saying, it's not just one Feynman diagram that matters, it's a whole bunch of them. Let's add them up, let's look at their effects. And I'll be interested to see what's possible with those kinds of approaches. Oh, there are some of Sebastian's very, very nice pictures. Well, so our next award here goes to Sebastian Mizera. And now I'm even more motivated to read your paper about the S matrix.
Thank you very much.
Our next award goes to Fei Du of the University of Illinois. She's in the accounting department at University of Illinois. And I know that her early introduction to Wolfram language from 4 or 5 years ago came through a curious route. Her son, who must have then been an early teenager, came to our data science boot camp. I think she came along as just to support her son. Her son got very involved with our technology, and so did she, and started using Wolfram language to do data science for accounting and to teach accounting students data science. I kind of think that, there was a time when when the main skill you needed to do accounting was good arithmetic. And when people like, Ramanujan were, clerks doing accounting, and he was really good at it because he was really good at doing arithmetic. Well, of course, that got automated. And then there were times when it was like, fill out the tax return and so on. And then a lot of that got automated. And I kind of think that the role of accountants has been more and more in the direction of what has been traditionally thought of as data science, sort of understanding, getting insight about numbers rather than doing the mechanics of the numbers. And Fei has developed a course at University of Illinois about data storytelling. Is that the name of the course? To teach future business folk how to understand those numbers, how to extract stories from those numbers. And she's been using Wolfram language and Mathematica for that, particularly making use of a bunch of the data that is part of the system to provide kind of real world examples, and for students to explore. And just last year, Faye published a book on creative data analytics that I gather she's using in her class, and it's now being adopted in a couple of other universities to sort of spread these ideas of computational thinking more broadly in the field of accounting and so on. And accounting has been sort of it made the jump from do it by hand to do it with using a spreadsheet, but the coming jump is surely to sort of computational accounting, where one can use Wolfram language and where one can express things in computational language. One can express the questions one's asking in computational language, and where one is able to, in just a few lines of code, be able to sort of ask the question and get the answer. So let's see, I gather Faye has been experimenting with chat-enabled notebooks and using LLMs to study these things. Let's see, did I forget? Oh, no, I am sharing my screen correctly. This is so confusing. This is so much easier in person. Well, so our next award goes to Fedu. Thank you.
Thank you very much, Stephen.
Our next award goes to Hector Benitez Perez of UNAM, National Autonomous University of Mexico. And Hector's background is in engineering, but Hector is now in charge of the Computing and Information Technologies Directorate of UNAM. UNAM, Hector was telling me, and I didn't realize just what a big university UNAM is. Apparently, it has 400,000 students, making it one of the very largest universities in the world. And it has students spread across all of Mexico. And Hector has been involved in setting up the technology and the content for teaching and making extensive use of Wolfram language, and has had a Wolfram Academy set up at UNAM to help spread knowledge of Wolfram language at UNAM. And I gather that they've had they just recently had a data science course that was desperately oversubscribed, which is always a good sign for these things. But Hector has been a major force in spreading computational thinking with Wolfram language at UNAM and in Mexico in general. And in addition to those activities, has also pursued his own research using Wolfram language. This is where my lack of knowledge of Spanish hurts me, because I'm looking at a lot of interesting content here that's in Spanish, and I'm not going to embarrass myself by getting it wrong here. But it's we are I gather that Hector has also been involved in setting up the technology to provide students wherever they may be with virtual machine access to our technology, so that they can make use of it in their courses, and also in collecting an organized setting up, having a mechanism for professors to learn about how to create course material using Wolfram language that can then be distributed to students who are making use of it in courses. So our next award goes to Hector Benitez Perez, and thank you for all your efforts and good uses of our technology.
Thank you, Stephen. Thank you very much, and thank you to my colleagues from the GETIC for all the effort that we've been doing these years. Thank you.
Thank you. As I say, our last award goes to the Europa Clipper Technical Resources Modeling Team. And their spacecraft, the Clipper spacecraft going to Europa, moon of Jupiter, just got launched on, what was it, the 14th, it's just a few days ago. So representing the team here is losing my place here, but now I'm going to say your name wrong if I don't see it written down. So I'm oh my gosh.
Narek Shigarian.
Thank you. Sorry about that.
Good.
The so it's I think it's been a decade of preparation of this mission, and there's probably a nail-biting last few days because the spacecraft was launched from Florida, and Florida just had a hurricane, and apparently the launch window for the spacecraft just opened right at the time when the eye of the hurricane passed over Cape Canaveral, but they didn't do the crazy thing of launching a giant spacecraft through the eye of the hurricane and waited, and it's now launched. And apparently the other members of this team couldn't join us because they are in the language of that business on console, because the things that they're working on are things that are actively happening on the spacecraft right now, and so they have to be the people actually sitting at the mission control, paying attention to what's really going on as the spacecraft gets ready for its trip to Jupiter. Actually, its trip to Jupiter is an interesting piece of celestial mechanics, because it's not going to Jupiter immediately. It's actually going towards Mars. It will get a gravity assist from Mars. Then it will actually come back to Earth, I think in 2026. And so it'll be back nearby. Maybe I don't know whether something went wrong with the spacecraft. I don't know whether anybody gets to repair it, or whether it's going too fast to catch as it goes past Earth. But then goes on its trip to Jupiter, arriving in 2030, and then is orbiting Jupiter, and is supposed to spend 3 years or so making flybys of Europa. And the excitement of Europa is there's probably liquid water on Europa, not on the surface, but underneath some number of kilometers or tens of kilometers of ice. The thought is there's liquid water down there. And the spacecraft has, I think, 10 different instruments that are intended to be able to detect the presence of liquid water. Liquid water, well, we know it worked on this planet to be a place where life could evolve. So gives us the chance to have Earth-like life somewhere else. I think it'll be, if there's a piece of RNA in that ever gets found by some creature that drills through the ice on Europa and makes it to that ocean, I'll not believe in independent origins for life on Europa or on Earth. But I think it is whatever it is that might be considered life is likely to be a lot more exotic. But it certainly helps to have life like on Earth if there's liquid water there. And so the Clipper team has been using particularly System Modeler for a number of years, initially to study power usage on the Clipper spacecraft, and subsequently to model all the subsystems of the Clipper spacecraft. I gather one of the things that was true about the spacecraft is most outer solar system spacecraft have used radionuclide energy sources where they have some plutonium or something, and as the plutonium decays, it produces heat, and that heat is harvested to produce electricity, a thermoelectric source of electricity. That's what's been used for most outer planet spacecraft. It's really difficult to get that much plutonium. The Clipper spacecraft is, I think, a 6-ton spacecraft, the largest one that's been launched into the outer solar system, and it's one couldn't get the fuel for it, so instead it has solar panels, and it needs to have really big solar panels to work at the at Jupiter, where the sun is not very bright. And so I think it has some solar panels which have now unfurled, I assume, successfully, size of what, a basketball field, something like that. The question is, when the solar panels and the big boom that sticks out of the spacecraft that has magnetometers on it, there was apparently an issue of whether the spacecraft could go in a particular configuration so that the magnetometers could operate and do their thing of measuring magnetic fields while there was still enough exposed area of the solar panels to be able to keep running the spacecraft. Well, I gather that nothing is easy when you're trying to launch a spacecraft to the outer solar system. Jupiter has the feature that it has a very strong magnetic field, and that strong magnetic field catches electrons and protons and produces a kind of super version of Earth's Van Allen radiation belts. And so the spacecraft is sort of inundated with radiation, and it has a little sort of vault made of aluminum where its computers and electronics reside. But even so, there can be ionizing radiation that penetrates and causes the computer to reset and so on. And I gather a bunch of work has been done with System Modeler to study the effects of those kinds of things. I was impressed to hear that when you're doing sort of outer solar system work, everything is planned. It's one kind of imagines things like rovers on Mars. It's like, that's an interesting rock, let's go and see, let's go drive to that rock type thing. And it's kind of done on the fly. But for the primary mission of something like Clipper, it's sort of all planned in advance. It's great to hear that System Modeler has been the tool that's been used to do a bunch of that planning, starting with the power system, and being able to somehow I'm reminded in talking about the power system of a spacecraft, things like the movie version, at least, of Apollo 13, and the difficulty of how do you power up a LEM or something while not using too much power or something like that. And I'm sure those kinds of problems exist in kind of mission planning for something like the Clipper spacecraft. And I gather that System Modeler has been used to try and make the modeling well, what happens if we turn on this instrument in this order? What happens if we do this or that? And that's a great use of systems engineering. I was commenting that I hope that the Clipper team will make the system model that is created of the spacecraft available broadly. It'll be a good way to recruit future space systems engineering folk. Anyway, so our and I also want to say that I gather the Clipper team has worked quite extensively with our system modeler team and asking for new features of system modeler and so on. And it's great to have a driver of things, because I think a lot of what system modeler is used for is terrestrial engineering. It's been used for some other space applications too, but mostly it's terrestrial engineering, and it's definitely not outer solar system engineering. So it's interesting to be driven in that direction. So our next award here, our last award, goes to the Europa Clipper Technical Resources Modeling Team.
Thank you very much. On behalf of the team, we're honored. Thank you.
Thank you. All right. Well, that concludes our Innovator Award presentation.